So what I'd like to do now is move on to our talk by Professor Ivan Baldry from Liverpool John Moore University. I would ask that everyone mutes their microphones, and if they want to, Ivan's very happy to take questions as the talk goes, but rather than shouting out, if you could type your questions on the chat facility, and I'll keep an eye on that. And if the questions are building up, or if you particularly want to stop Ivan and ask him a question, if you'd let me keep an eye on the chat, and I'll take it upon myself to ask Ivan to address particular questions. So I think Ivan has already introduced himself and his journey around the globe to get from his starting his astronomy career with his undergraduate studies at University of Cambridge to ending up being a professor at Liverpool John Moore University. And he's going to talk to us tonight about galaxy populations and the colour of the universe. So thank you very much, Ivan. If you want to take the screen from Carolyn and give us your talk. I think you need to unmute your microphone.
I'm unmuted now.
That's great.
Do I press view slideshow? Can you see my PowerPoint now?
Yes.
What's the normal thing? You press view slideshow, do you?
I think so.
And that still works? Yes. That sees the full screen now, yeah?
Yeah.
Okay, galaxy populations and the color of the universe. Well, actually, I got 15 minutes of fame for the color of the universe. I don't know if anyone remembers, but I'll explain about that back from when I was at Johns Hopkins. Okay, so I'm going to be talking about galaxies, which mostly you can't see with a backyard telescope. Of course, there is one or two, but these are very large distances. First of all, I will give a little reminder of units and so forth that I'm going to be using. And then I'll talk about my general field of galaxy population statistics. You've got to get the excitement by looking at a graph rather than an image. So we've got to get some of that worked out, particularly concentrating on low luminosity galaxies. They don't look much to look at, but there's many, many, many of them. And then the color of the universe revisited, so a bit of fun at the end there. Sorry, I'll do this. Okay, so units. The first one we need to understand if we're a cosmologist is megaparsec. It's historically parsecs have been used rather than light years. So, but anyway, if we're think of light years, that's about 3 million light years, or probably a more useful way to think of it. It's the distance to our Andromeda galaxy is 0.8 megaparsecs, and it's the most distant object you can see with the naked eye. I'm sure many of you have seen that. If you've got a very dark site somewhere you can go to, it's on the left there. And then we've also got a map of a local group of galaxies, and now we've got a scale bar showing 6 megaparsecs. So right at the center, we've got, you can see my cursor, okay? Yeah, M31, which is the other name of the Andromeda galaxy, and us at the center, and then some dwarf galaxies here. The Large Magellanic Clouds and the small, which can be seen from the southern hemisphere. And then several dozens of galaxies in that 6 megaparsec sphere. And then the next scale I'm going to talk about, which is really an important scale for cosmology, is what I'm going to this is a unit I'm using here and nowhere else. Well, I've used it once before, and it's a sort of I'm going to call it the cosmic volume, a cosmological volume. So I'm going to abbreviate it CosV, and it is basically 100 by 100 by 100 megaparsecs box of the universe. And if you want it in megaparsecs cubed, that would be 10 to the 6 megaparsecs cubed. I've realized I've missed one slide here. and that's exponential notation. Do you want a reminder, or are you all happy with that?
No, we're good.
I think most people should be happy with that.
Yeah. Okay. Exponential notation, 10 to the 6 megaparsecs cubed, and this, well, it's very hard to see this. You can make a map, though I do make a map of the universe, but here's one from a simulation, which is 43 megaparsecs on a side box. And each of those little dots of lights is a galaxy or gas associated with a galaxy. And so you can see you're looking, this is the type of scale of the universe I'm working with when I'm doing statistics. It's a very large scale where there are millions of galaxies. 80,000 megaparsec cube, that is that box, or 0.08 cos v. And the mass of the other unit, mass of the sun, well, that's one we can understand. And for comparison, our galaxy has a mass of about 5 times 10 to the 10 solar masses. That's the stellar mass. That's not including the dark matter. And a globular cluster you can see with a telescope has a mass of about 5 times 10 to the 5, or 500,000 solar masses. And so where do I fit in this picture? You might have heard talks on a range of these things, all different scales. From the higher scale, we've got cosmology, we've got galaxy populations, which I'm going to talk about. We've got individual galaxies. Within a galaxy, you've got interstellar medium, and then people look at stellar populations, and then right down in our local backyard, we've got the solar system. But here I'm going to be talking about this thing. So just below cosmology, but talking about galaxies as a population and not individual galaxies. So why do I have a box of 100 by 100? Well, at the beginning of this GIF, the galaxies were shown in their true positions in a box size that was 700 by 400 megaparsecs with 100 megaparsecs depth. And what I've done here is I've gradually removed the galaxies from their original position in a random direction. And you can see how far they are moving by the blue bar on the top. You got that? So what happens is, as you perturb the position of the galaxy in a random direction, when it looks smooth, then you can say that perturbation is kind of giving you a homogeneous picture. Yeah. So when that reaches a scale of about 100 megaparsecs. So roughly speaking, 1 cos v, and this is a map of covering 28 cos v, is the same as another bit of the universe of cos v. So in 100 megaparsecs boxes, cos v boxes, one part of the universe is homogeneous, has a similar population of galaxies to another part of the universe. Okay, so there isn't statistically any difference between, well, depending on what galaxy population look at, there isn't a lot of difference between one cos v compared to another cos v. And believe you me, there are many cos v in that. So it looks smooth. It's not, and it's definitely not fractal, which would be the other possible distribution. And the other thing is, when we do cosmology or galaxy evolution, the further we look back, we're looking at a picture of the timeline of the universe. So if we could measure galaxy populations closer to the Big Bang and compare them to galaxy populations nearby, when I say nearby, I'm still talking about millions of light years. But then we're looking at effectively looking at the evolution of the universe as a whole, statistically, because one cos v is the same as another, statistically, that is. Okay, so that's why we measure the population of galaxies. So, and we can also see the population of galaxies evolve in a way that you can't do in many other areas of astronomy. You can't see individual stars evolve, but you can infer how they've evolved, but you can't see them evolve, generally speaking. But with the galaxy population, we can see it evolve. As we look back in time, we see a different set of galaxies to today. So galaxy population statistics that way is what I'm interested in, and it sounds a mundane thing to do. Count galaxies and measure the galaxies' properties over a volume of space, but actually quite tricky. There are all sorts of observational effects and problems needed to solve, but I won't go into too many details. So with that, we can compare with observed galaxy population between different epochs, which I've just mentioned, looking at them, how they've evolved, or we can compare with simulations of galaxy evolution with dark matter. And so the other major property of galaxies, not just the number of them, but is each one's mass. So here I've written down the exponent of the mass in solar masses. So on the one here, which says 11.0, that means it's a galaxy that's 10 to the 11 solar masses. And the one down here, about 10 to the 10, is a Milky Way, or 10 to the 10.5 is about a Milky Way sized galaxy. And then we've got getting smaller and smaller, 10 to the 9 down here, 9.0 is about the Large Magellanic Cloud sized galaxy. And then there are lots and lots of smaller galaxies. And these are all on the same scale. And they're fuzzy little blobs in the sky. But there's many, many, many of them. And so counting them is what we do, and counting them by mass is the second thing we do. Just a reminder, I'm counting galaxies in a CosV. It's a very, very, very large volume, or if you like it, it's 5 times 10 to the 76 pints. I'm sure that'll be a very useful unit for people to use. You can count the number of zeros there, or if you want to look at, you can look it up in 50 quattuorvintillion pints. But anyway, how many galaxies are there? I think a CosV is probably the easiest way to think about it. Well, this is what we call then a mass function. So this is why you have to get excited by graphs. On this side, on the y-axis, we have the number of galaxies per CosV, and per each of these bins. What I mean is the width of the bar here, 0.5. And on this axis, I have the galaxy mass going from 10 to the 6 up to 10 to the 12. And so this basically covers most of the galaxies range that we know about, really, so far. We've got the very massive galaxies that are rare. There's like 3 in a CosV. And then we've got our Milky Way galaxies around here, which are about 2,000 in a CosV. And then we've got our LMC galaxies around here, and we've got about, 5,000 per CosV. And then we've got these dwarf galaxies down here, and there's more than 10,000 per CosV. But they're not very easy to see. And so actually, a lot of these are missing from our surveys. Oops. And just to be clear here, there are 2 types of dwarf galaxies. There are dwarf spheroidals, which we can see near our Milky Way, and they're star-forming irregular galaxies, which are blue, full of gas, have young stars. And the lower ones are the ones I'm talking about, because they're actually far more common in the universe, probably, and they're certainly, and they're dotted between the enormous the giant galaxies like the Milky Way. They're just spread out between them, basically. And you can see them here, a whole collage of them. And these are all of about the same mass in stars. So about 3 million to 10 million solar masses. and they're all about, these ones are all about the same distance. And you can see here there are ones that are easy to spot because they're very bright. Sorry, they're centrally concentrated, and there are ones that have the same mass but they're all spread out. And these are actually hard to detect because you take camera pictures of the sky and these galaxies, and you're covering billions and billions of pixels of information, and finding them automatically is very hard. So the question is, can we find a different way? How many galaxies are there per cos-v? And we're considering only the star-forming galaxies. So we need to find and measure these faint galaxies. And one way I came up with a few years ago, was to use supernova. Now, it sounds strange, but I'll explain why it works in some ways. When a supernova goes off, it can outshine a dwarf galaxy for a period of weeks. So this isn't a dwarf galaxy on the left, this is a giant galaxy, but it does show the image of the supernova that's gone off in the galaxy, and it's easy to detect in imaging. What I'm going to specifically talk about is these types of supernova. They're called core collapse supernova. What I've got here is a diagram showing the time scale for how stars evolve. A massive star evolves. By mass, I mean 25 solar masses. Burns hydrogen to helium in about 1 million years, and then the nuclear burning rapidly proceeds up the chart up to iron. And then finally, it collapses as what's called a core collapse supernova and gives out a lot of light. And these high mass stars are only young by the standards of astronomy, and therefore they only occur in galaxies that have recent or ongoing star formation. They're not often can be found, but we can, if we look at an entire volume of space, let's say cos-v of space, we can measure how many supernovae there are going off every year. And this project I did with my student, Tom Sedgwick, who's will graduate this year, or next year, sorry, 2021, and Professor Phil James and my postdoc I used to have who moved to America, Lee Kelvin. And
Ivan, can you take a question from Kevin about some of the observation issues associated with your talk?
Yeah.
Kevin? Is Kevin listening?
I am.
Good.
I might be about to find out the answer to my questions, because that's the Sloan Digital Sky Survey.
Well, go on. Pose your questions.
You'd mentioned that you had some observation issues, especially around the faint galaxies. How did you overcome those in the end, or is that what you're about to talk about?
Yes, that's what I'm going to talk about.
I should hold my questions till the end.
It's the problem is that when a galaxy, like a dwarf galaxy, is faint, it's also spread out, and therefore it kind of merges into the sky. And so they're very hard to detect. So what I'm going to do is we use supernova as signposts towards galaxies, and did that using a very old survey, but where the data was available and hadn't been used in this way before. And they did a special survey called the Stripe 82 survey, where they imaged the same stripe of sky every few days for 3 years when possible. Mm-hmm. In fact, it was probably amounted to about a year's worth of survey of the supernova. And then this did two things. It allowed them to find the supernova, and it also allowed them to stack images on top of each other to increase their sensitivity. Okay. And so we detected about 2,500 host galaxies as supernova that were in our preferred distance range, and that amounted to about 100 per year per cos-v. That was our calculation, and that was in agreement with what other estimates of what we call the cosmic star formation rate that is about 10,000 solar masses of stars form every year in a volume the size of cosV, across all galaxies, that is. So that's something called cosmic star formation rate. And so what we've got here is on the top, an image, a normal image of SDSS with the location of the galaxy. The second one where the supernova has gone off, it's still quite faint, but it's at least detectable. And the third one where the galaxy has been found at the location in this sort of co-added imaging, we call it, where the imaging is a little bit deeper. So effectively a longer exposure.
That's incredible.
And there's another example on the bottom where this galaxy has been detected.
So that's like when we amateur astronomers tend to use stacking to get slightly deeper field of view and bring out some of the brilliant.
It's exactly the same, yeah. Yeah, stacking is probably 80 or so images, up to 100 maybe.
Incredible.
To bring out the deeper data. Of course, there are bigger telescopes that can do better now sort of, but it's always problematic finding low surface brightness galaxies because the automatic algorithms that go through them and try and locate all the galaxies, it's very easy to get confused with noise, with the location of a galaxy, sorry, a dwarf galaxy, and something else that's an artifact of the imaging processing. You know, there was diffraction spikes and scattered light and so forth.
Yeah.
So you know that's really tricky to separate them. But if you know a supernova's gone off, you know where to look. That was the idea anyway. That was basically the idea of our survey, was find out all the supernova in a given volume of space and go look at every single one. And if a galaxy hadn't already been detected, go and find it and measure it. That was the basic plan.
Because you've got to have some sort of galaxy or concentration of stars to, in most cases, to have a supernova. Otherwise, you've got a wandering star in the interstellar medium that's got no galaxy, which seems a bit odd.
Intergalactic medium.
Intergalactic medium, even, yeah.
Yeah, so it's likely that they're associated with galaxies. They could be on the outskirts of big galaxies, or they could be on dwarf galaxies. In this case, we associate them with dwarf galaxies here. Two obvious, well, once we've got the stacked images, dwarf galaxies. But can we use that to calculate how many galaxies there are? Well, it's kind of a tricky argument, but this is the argument that I developed. There isn't a supernova every year in a galaxy, okay? There hasn't been one in the Milky Way since we've been looking. Well, there are historical ones, but it's hard to measure it in the Milky Way because of the dust anyway. But in a galaxy of about 10 to the 7, we expect it to have formed over its stars over at least the age of the universe, roughly. So we only expect 100 solar masses of stars formed per 100,000 years, which means if you do the calculations of what types of stars form and when they form, you'd expect only one supernova every 100,000 years in this type of galaxy. But we can, assuming that argument's correct, if we do count the number of supernovae and measure the galaxies, we can then work backwards and say, well, if we've seen, for every single supernova we see in this type of galaxy, there must have been 100,000. Okay? And then we divide by the volume and we infer the number of galaxies. This survey we covered more than one cosV, maybe even 50 or so. I can't remember the exact details. Actually, it'll be here when it's 2,500. Yeah, sorry. 2,500, and there's 100 per year. It's about a year survey, so about 25 cosV was the size of the survey. Anyway, you do work out the number of galaxies per cosV, and these were our results up here in the dashed line. And you can see that we, as expected, or possibly as expected, the number of galaxies of these small galaxies is implied to still keep rising, and that we're looking at something like 50 or 100,000 galaxies per cos-v for in these regions here. And that was higher than these numbers which were measured from direct surveys, which hadn't used the signpost method for supernova. So, how many galaxies are there in the universe? That is sometimes asked. And, well, to answer that question, you actually have to set a lower limit because we don't know how many galaxies there are below 10 to the 6 or 10 to the 5. So I'm going to set a limit of 10 to the 7 to be on the safe side. Then I add up all the galaxies from our method that are implied to be in that volume, and I would say there was about 80,000 per cos-v. The numbers in the range of the 10 to the 6 to the 10 to the 7 is probably still uncertain. And then you can work out the size of the universe. Well, the only thing we can measure is the observable universe. And that is about 10,000 megaparsecs distance away. And then you work out the volume and you get about 3 times 10 to the 11 galaxies above this 10 to the 7 limit. So that's about 300 billion in the observable universe. Whoops. Okay, so that's the first bit. Now I'm going to go on to the color of the universe revisited part of the talk. So I was talking about the galaxies down here and how hard they were to measure and how we use supernova as signposts to these galaxies. Now I'm going to be talking about where most of the light comes from. Most of the light clearly doesn't come from the galaxies down here, even though there are so many of them, because otherwise they'd be easier to see, if you like. Yeah, there's a lot of them, but they don't produce much light compared to these ones. So most of the light in the universe comes from these galaxies. It doesn't come from these ones because even though they've produced a lot of light, they're very rare. It comes from one galaxies around the size of the Milky Way. Okay, so you can measure their light using spectroscopy, spread out the light like the rainbow, in fact, except you spread out the light into even finer bands, and you measure a spectrum that represents the universe by adding up the spectra from all the galaxies that contribute to that light, the main part of the universe, the main part of the light emitting universe. And you can measure elements like calcium, sodium, magnesium, iron, and here we define it as the light emitted per unit volume of the universe in the cos-v. And that's what it looks like. It looks fairly close to actually the spectrum of a typical, it's just a spectrum of a typical galaxy. And some of these features are in the sun. The sun doesn't have emission lines. That is lines that are brighter than the continuum. The emission lines are actually caused by gas that's being heated up in the galaxies, but the sun also has absorption lines due to the higher than helium, due to these common elements, sodium, magnesium, and calcium. And here's a sort of a normal sort of a rainbow picture of the same spectrum.
Is there 2 hydrogen lines on there for a reason?
I think it's hydrogen and sodium, actually.
Okay.
Cool. Yeah, it is. So how do we know it represents the universe? We measure many galaxies from the bright to faint end, and we determine that the galaxies that we're missing down the very faint end don't contribute much light. Clearly they don't, because they're so hard to detect. And it tells us about the history of star formation in the universe, the metallicities, and we can also calculate the color as perceived by the human eye. And so this I did with a colleague called Carl Glazebrook back in 2001 or something like that. And what we did was we imagined looking down at this average color of this average spectrum of the universe from some vantage point in space, looking at the average, and then you calculate what the color would be as looked at by the human eye. And to do that, you take what's something called the CIE coordinates, which are kind of like a representation of how your eye would see that's hue. Is that the right term? Yeah, the hue of the
that's
color.
right.
Yeah. So red filter, green filter, and blue. This isn't quite. It's a complicated science. This is called color science. I'm not an expert in it, but this is one way to represent the visual perception of the light that you see. And then you calculate that, and we get an X value and a Y value, and then we compute that to an RGP that you'd see on a computer, and you need to give a coordinates of a white point as well. And to do that, then we calculate the color, and we came up with, well,
Orangey pink.
well, rather embarrassingly, the first time we used a piece of code that was incorrect, and we came up with turquoise. There was actually, and that turquoise color actually appeared on the front page of the New York Times. And then we had to, about a month later, correct it and say it was beige. Because, and it is, yeah, if you pick up what's called a E white point, then it comes out as beige and or cosmic latte. Cosmic latte, actually, there's a Wikipedia entry for cosmic latte if you want to look at that. And yeah, it's rather boring color, but that's the way it is. And yeah, of course that's that maximum brightness. But this topic was revisited when I was contacted by an artist, and this was more interesting in many ways. An artist called Katie Patterson. It was Katie Patterson Studio. Well, I was contacted by one of the people working there, and they wanted to visualize the color of the universe, not just for the present day, but from the Big Bang to the Dark Ages, to the first stars, and present day, and to the far future. I thought, oh, this is really cool. I thought, let's give this a go and help them calculate the numbers. So that's what I did. And the early universe is actually really easy.
It's all blue light.
Because it's all what's called black body spectra. That's perfect, and they're given by these black lines here. So the black line shows the intensity versus wavelength, the big thick black line. What also showing here is the RGB filters. And then I've also coded the light that would appear. So in the early universe, it starts out blue when it's, this is before the Dark Ages, before there were any stars, and then it gradually fades and becomes redder and redder. And in fact, it's, until the first stars form. So this is just gas cooling as the universe expands. And then the stars form. So this was the early phase before stars. And then the stars form, and when you're dominated by young stars, they appear blue. So here's a plot of what's called the Hertzsprung-Russell diagram, which is just basically the luminosity of the galaxy, of the star along here, and the color, the star along this axis, or the temperature rather, so high temperature and low temperature. And when the galaxies are all young, they all appear very blue, and as you get older and older galaxies, they appear redder. Okay, so as we go towards the present day, we've got a mixture of old and young galaxies that are still forming stars and galaxies that have stopped forming stars. But in the early universe, after the first stars formed, they were all appeared blue. And so this wheel was developed. It's not linear in time, but she got the color onto this wheel. That's her on the left there on that picture with me. And I sent the calculations of the color, and she made the wheel and had an exhibit with explanation going from, so the early universe going from blue down to red, and then the first stars form, blue, yellow, and then I had to think about, it wasn't only me, what would happen in the far future. Well, as it turns out, the gas, it's very likely that galaxies run out of gas. Galaxies are flying apart, they don't get more gas, and the stars get older and older, and the stars are like half a solar mass that are left, and they're all red, and that's so this is a trillion years in the future kind of prediction. And this was our present day, and this was this is not linear in time, but there's an explanation for it, of how it happens. And it was made into what it actually looks like is a wheel that spins round. This was how it was made. Can you see that? I'm sharing my video screen now.
Yes, we can see.
Yes, we can see that.
Yeah. And it was,
that's incredible.
so yeah, it was showing a real speed, and I've also slowed it down with the. So this is what it actually span round at, and then this is with the camera using a time-lapse photography of it spinning round. So this was in an exhibit in Margate. Margate? Is that the right name? And the one on the south coast somewhere. Is that Margate?
Margate's in Kent on the south coast.
Yeah, that's it. Yeah, I went to Kent. Yes. But and then it would have moved up to Edinburgh, I think. But Katie Paterson's Scottish, so I think the exhibit went to Edinburgh after that. I don't know if the colour wheel is being shown anywhere else still. Okay. She also likes to do a lot of other stuff with astronomy, which is really fun as well. So look out for her doing her artwork if you're interested. And so, all right, summary. I can stop. Wrap it up here. Well, this is my summary here. This is my graph that I'm most interested in. The exciting plot that shows the number of galaxies per bin, per cosmic volume of a universe, CosV. And we've used supernova as signpost to very faint galaxies. This is a reminder here, and that allows us to calculate the number of star-forming galaxies up here. And then I've also looked at the most brightest galaxy, and that calculates the color of the universe at the present time. And then using models, you can calculate the color of the universe through time, which gives a nice visual impression of, and can be used to relate art and science education, really. And that's what I talked about. Thank you.
Ivan, thank you. I love the way you brought your talk to a conclusion with the help of the artist and the color of the universe. It was very, very, very visual, very impressive. Thank you. There were some questions. There were two people wondering about how you were assisted by the Galaxy Zoo program at all.
I have
classification of the galaxies. That's what we're thinking. The color of the universe was calculated before the Galaxy Zoo project. I have worked with the Galaxy Zoo data when I've looked at a different project, which was to look at how galaxy properties change as they go towards the center of a cluster of galaxies. And for that, we use Galaxy Zoo data to estimate number of ellipticals versus the number of spirals. So I have used Galaxy Zoo data indeed, but not for this particular work. And I've also been involved in other projects looking at Galaxy Zoo data as well.
So does anyone else want to ask any questions of Ivan? You showed the photograph of a telescope. Which telescope was that?
That was the Sloan Digital Sky Survey.
So where is that?
I'll go back one sec. That's in the United States of America.
Right.
I worked on this project when I was in the Johns Hopkins University. I think it's Apache Point Observatory, which is in New Mexico, maybe.
Mm-hmm.
And it was the first large area digital sky survey, basically using modern charged coupled devices, CCD cameras. And it used about 30 chips on the camera, and it used 5 different colors and so forth. And it used a method of observing called drift scan, where they didn't actually move the telescope. They let the sky go over the telescope, and then the charge from the detectors read out the same speed that the sky was going over.
Well, that's a neat idea.
I think that's the way it works. So it got exactly a 55-second exposure, which was the length of the sidereal time, the sidereal crossing of this time as it read out over the detector chip. But it made for very accurate. It actually was a pretty good survey for keeping the sky background under control and avoiding. It was very clean images, even if they weren't that deep. They weren't deep until you did the co-adding. I mean, we're looking at new surveys coming up, which are enormous by comparison. I mean, Large Survey Synoptic Telescope, Rubin Observatory.
That survey is done by other telescopes.
Sorry, which survey?
The survey. Sorry, the survey you just referred to.
Sorry, the new surveys coming up.
Yes.
Yeah, there's a telescope being built called the Rubin Observatory, which
Vera Rubin.
Yeah, no, it was renamed after Vera Rubin. It was originally called the Large Survey Synoptic Telescope.
We had a talk earlier this year by 2 people from California about that and the influence of the Starlink program on their observations.
This telescope hasn't got running yet, but it's like a 10-meter aperture, and it's got like 100 detector chips eventually. I don't know. It's absolutely enormous. The camera is mind-bogglingly huge. They're not even going to put the main camera on to start with. They're going to have a trial camera before they go up to the full-size camera. But it'll be able to observe a whole sky every night, something like this.
Thank you. Does anyone else want to ask any questions of Ivan?
I was just having a quick look, and all of the data from Sloan Sky Survey is available to peruse, which I think is just incredible.
Yes, you can. They've got a pretty good navigator, so you can zoom in and out on the images. They don't cover the whole sky, so you still have to go to the Digital Sky Survey if you want, the Digital Sky Survey is a digitized photographic plates, but if you want, you get better quality images from the Sloan Digital Sky Survey over a fair fraction of the sky.
It's just an incredible instrument. Genius idea to just point it at a piece of sky and watch, and rather than sort of steering it, just let the sky do the moving.
Yes.
That's an incredible idea.
Yeah, I mean, I don't know how they programmed that, but they did.
So how long has that telescope been in operation for?
It's evolved into different experiments. Basically, they only concentrate on spectroscopy now, But I guess it's been going 20 years, yeah.
Mhm.
Yeah, they've got a spectroscopy component, which has then expanded, and now that's where they now have spectra of galaxies, of different parts of the same galaxy, and so forth. I could show you one more thing here. This is a rotating cone of positions of galaxies. It's pretty slow for some reason. I don't know why I remember it being that slow. Or from a different survey of galaxies, but it shows you the locations of how galaxies are in relation to each other, and that the lower mass galaxies are more frequent.
Is that because they're newer galaxies in essence, either created through galaxy interactions or just?
No, I don't think so. I think most galaxies have been forming since at least 10 billion years.
Yeah.
It's just that
the stars within them
all the galaxies are. Let's go back to the. Let's have a look. Yeah, all the galaxies in this sort of range are all star forming, and mostly star forming, and mostly have probably been forming stars for about 10 billion years, though they may have formed more stars recently. But there's no such thing as I don't think we've ever for sure seen something that's just a perfectly new galaxy, although at least they'll be very rare.
Yeah, because you would expect galaxies to evolve over a significant period of time for the size and the mass that you have to coalesce in order to create the star formation regions, which ultimately give it the light. Otherwise, it's just black dust.
And so we think that they formed from the collapse of dark matter in the early universe, and that those are the locations of the galaxies. There are some weird, freaky cases, like in a very high group of cluster of galaxies, you might find two galaxies that collide together, and a wispy bit comes off and forms some stars, and that might be called a tidal tail galaxy or something like this. But those things are kind of pathologically unusual.
Well, Ivan, thank you very much.